All set. You guys have to press the button.
Yeah. I had the same thing.
Use two buttons.
Get over.
All right. Hi everyone. So, first thing, what's the first fundamental theorem of Calc 3? You guys remember?
Smile.
Nah, you can't smile all the time. Sometimes you feel like that. The first one in the syllabus, right? What was the first fundamental theorem of Calc 3?
Have fun.
I mean, implicitly, yes. No, it was a. Did you guys not read the syllabus?
It's a math class and a reading class.
Yeah, no, but it was a reading part in a math one. It wasn't even a math equation. The first fundamental theorem of Calc 3 that you learned about before we even started doing any math. There were 3 fundamental theorems of Calc 3.
It needs to social nature.
Aha. Well, I forget the order. Nothing is supposed to be interesting. Nothing is supposed to be obvious. And then what's the third one? There's no such thing as a stupid question. So I have a 3D printer at home. And it has a build plate. This thing gets heated, and then basically a glorified hot glue gun with a motor attached to it, well, 2 motors, X and Y, right, parametric equations, decides to deposit melted stuff onto this. So I used this, and I really wanted to make little, chalk holders. But it got really hot, there was a clog, and all of the material stuck to this overnight and left a residue. So when I peeled it off, it took a bunch of the material with it. And if this doesn't have the right texture, it won't hold the melted plastic. Does that make sense? It's a glorified hot glue gun, yeah. Unlike a hot glue gun where the hot glue sticks to anything and the threads follow you everywhere like you're Spider-Man knowing about his superpowers. So I went on Amazon and I bought 2 replacements. And then yesterday, as I was about to put the new replacement in, I realized something. Nothing is supposed to be obvious. So if you think that someone is standing in front of this lecture hall because they know exactly what they're doing in life and they know what's up and they have everything figured out, I promise you that this is not the case. And so I will carry this with me. I'm not even hanging it as a plaque. To remind myself and others that nothing is supposed to be obvious. Because and the funny thing is, I removed this from the print and I was literally looking at this and it didn't occur to me, oh, it's like a 2-year-old playing peekaboo, right? They think you actually disappeared. All right, so, yes. And on that note, I wrote the exam. It's going to be fun. It'll be good. What was that? Oh, it says it's exam related. I need to bring these to you. M&M's. Okay. What was I going to say? Practice exams I will post at some point. Maybe once you guys are done with chemistry. I have some catching up to do. What's up?
How many?
How many exam problems? Oh,
How many exams? Practice.
Oh, it might just be one with like 20 questions. It's more exam-style problems. The exam will have 4 questions. You have an hour and a half, yeah? Unless you got other accommodations. It'll be okay. The goal is that this won't scare you. You might even laugh a little bit while you're taking it. If that works out, then I will have done my job. Okay, are we all good? Are we ready to talk about chain? Probably chain. And the Hessians, was it Hessian? Was it Hessian? The Hess truck, the orange, because it's the green. No, not Hess as well. Hess keeps that chemistry away from here. Hess is all chemistry. Okay.
Yeah, it's about chemistry, guys.
All right. So, review, yeah? Provided you're all not there. Are you all burnt out, by the way? It's the time of the semester.
Yeah.
Oh, wait, you can just the physics exam?
Yeah.
Oh, God, how'd that go?
Next question.
All right, so Jacobians. Yeah, no, I'm happy to chat. Okay, so what did we say last time? We said we had a vector-valued function f, which is a function that contains, it's a function that has got 2 components. In this case, maybe u of xy or v of xy. Notationally, what is this the same thing as writing? So angle brackets, yeah? U of xy, v of xy. And all this is saying is, this is a function that has 2 components, as opposed to 1. Historically, we've only done scalar value functions. We are now doing vector value functions. And we ask ourselves, well, what the heck is the derivative of this? And what do we say it was?
Jacobian.
Yes, so Jacobian is the derivative of this. So we say Jacobian of u xy v of xy. Another notation that we might say is this is oh no, that's fine. But how do we find it? What is it? Is it a vector? Is it a matrix? Is it a scalar?
We're doing grad of each of our vectors.
We're doing a grad of each of our vectors. So we have two components, u and v, and they each depend on x and y. Yes? So this is u, this is v. And actually, notationally, I will say one more thing. This is probably the best way to write it that will keep your ducks in a row. duv dxy. This is extending the idea of the partial derivatives to a higher dimensional situation. And if I'm going to be clean, which I always intend to be, I'm very thorough when I clean myself, just like a chinchilla. You think chinchillas because the rodents are dirty, but they are obsessed with keeping clean. Hi David, keep me on track.
So the UV goes on the top. So whatever's on the bottom with respect to the del is like, I'm going from those coordinates to these.
Yes, spoiler alert. But yes, that's generally the
Sorry.
sorry, no, that's kind of the right idea. It doesn't have the ability to be too much of a spoiler at this point anyway. Okay, and lastly, what is this? The first row of it is the gradient of u with respect to xy. And the second one is the gradient of v, no, not v vector, with respect to xy. What are the dimensions of this matrix in this particular case? 2 by 2, and now 2 rows, 2 columns, and tell me the individual elements. What is this?
Del x u.
Yeah, dvx, dvy, and if I want to be clean, let me use my triple equal sign, u sub x, u sub y, d sub x, d sub y. Okay. The position of these matters. So it's important to remember. The first function is the first row whose derivatives you take. The second function is the second function. Second row is the second function whose derivatives you take. There are special cases where the orientation might not matter. Spoiler alert. But we'll talk about that in a moment. Are there any questions about the Jacobian? Okay, so why is this useful? Well, first thing I want to say about this is we need to be careful about our direction. You will want to, wherever possible, and look, I even screwed up, uv to xy, you want to declare what is the derivative of what with respect to what. This is a really clean way to do it. This is fine, uv to xy, that's fine. It's taking, you're taking the derivatives of u and v with respect to x and y, not the other way around. And this becomes interesting when we start chaining things together. Here's the question. Let's say that f, because all these high dimensional things that we talk about can boil down to a lower dimension. So this should reduce to what we're used to when we have a function that we're more accustomed to. We're not used to vector value functions. What are we used to? Scalar value function. f of xy is x squared plus y squared. My question to you is, does this reduce to what we expect it to reduce to when f is a scalar value function? If f is a scalar value function, what does this look like instead?
Just partial derivative.
Well, but the function itself, it wouldn't have a u and a v. It would just have it's the first thing, a u of xy. If scalar, it would just be u of xy. So one scalar function of two variables. Okay, so let's follow that path. What does the Jacobian look like when I have a scalar valued function? How many variables do we have? One. So what is the Jacobian look like? One row. What do we call that row of partial derivatives?
To building occupants, MIT Electrical Services will be conducting a test of the building fire alarm system. Unless you are instructed otherwise, please disregard all fire alarm alert tones, voice messages, and flashing lights.
We can
At
just
the
put that
conclusion of
ourselves,
this
right?
testing, an announcement will be made
know
to
that those
indicate
two-
that all fire alarm
we can
testing
put it out.
has been completed.
Good engineer, a way to make it stronger. Okay,
Attention
so
building occupants.
Oh, no. Wow,
MIT
okay, well, yeah, that's gonna be the
Electrical
whole class.
Services will be conducting a test of the building fire alarm
Wait.
system.
yeah.
Unless you are instructed otherwise, Please disregard all fire alarm alert tones, voice
Are you
messages,
also
and
gonna
flashing
finish
lights.
your question until that's
Yeah.
Testing.
So does
An
F-
announcement will be made to indicate that
when
all
you're talking
fire
about
alarm
making the graph
testing has
F,
been
that means
completed.
you start with the scalar and you plug in the parameterizations into F.
Attention building
Well,
occupants.
F- so,
MIT Electrical Services will be conducting a test of the
It's
building
like,
fire alarm
it's,
system.
from what we're used to, this is just
Unless
called
you
F
are
itself.
instructed otherwise,
So yes, it
please
boils down
disregard
to
all fire
DF.
alarm alert tones,
DX.
voice messages,
Is that
and flashing
response
lights.
different than if
At
you
the
take it
conclusion
one
of
step
this
at a
testing,
time?
an announcement will be
You have
made
to
to
do like
indicate
the-
that all fire alarm testing
I
has
think
been
it works, we did
completed.
X, Y, and Z,
Yeah,
and we did that Jacobian, but then we also did W, which is also in terms of X.
yeah, okay, so hang tight on that, because that's a chain rule thing.
Okay.
So, yeah, not a bad question at all, no, there's no bad. It's just, I'm gonna get to that.
A slightly better question.
Yeah, there you go. Okay, so are any questions here? People good? Okay, cool. Oh, I went rock climbing yesterday again, I ran into Ash. I hope I run into you guys at some point. Okay, so what are we gonna do now that we've done this? Let's say, so let's add to the mix. And say that x itself is a function of two variables, t and s, and y is a function of t and s. Okay. So now what do we have? We have f of x, which x itself is a function of t and s. One way to approach this is like saying that g, g, a vector valued function of t and s, what are the components of g of t and s? Yes, they are t and s, but it's not ts here.
It's S, it's
It's x of ts, y of ts. So, f is a function of u and v, and x and y are functions of t and s. Okay, now let's find the Jacobian. What is the Jacobian? xy going to ts, otherwise written as d xy, and what goes at the bottom? ts. Okay, let's find that. What are the components of this? So what are the rows when I do my Jacobian?
T and S. I mean, X and Y are the rows, T and S are the columns.
Sure,
So,
but the row of a Jacobian, each row of a Jacobian represents the what? The gradient of what? Of each row. Okay, so the first row is going to be the gradient of x. So what is the first element here? dx by d, t, next,
X, yes.
dy, yeah? Am I right or am I wrong?
Oh, yes.
Am I right? I don't have to be right, I don't have to be wrong. You don't agree? Who disagrees? Yeah, alright, fine. You tell me, what's up? What did I do wrong?
It's not, it's both of them are fine.
They're both of them with respect to x, yes. Okay, what goes here?
Yes.
Okay, next up. dy by dt, dy by dx. Okay. And now, so we have two Jacobians. I'm going to box these to sound like that. So I'm going to box them.
True.
This is j uv, xy is this. Okay? And what I would like to do now is I want to multiply these two out. So I'm going to say I'm going to say j uv xy multiplied by j xy to ts, which is notationally the same thing as saying duv by, I'm walking through this, duv by,
D, X, Y.
okay, times?
Times D, X, Y.
Oh, you can use buttons, you d, x, y.
D, U, V. Oh,
TS, yeah? Okay. What do your brains want to do here? What do you want to abuse some notation?
Cross out the x and y.
Yeah, but I don't believe you. So we're going to need to multiply it out just once. So dx, can people, wait, du dx, can you guys say it out? Du dx.
Du dy.
Okay. Yeah, help them out. V dy.
Wait.
Okay, what's next? Samples, what do you got? dx dt. Yeah, come on, samples. dx dt, dx ds, and then you got it.
You're getting your thing out.
Yes. All right.
Ooh.
Noah approves.
You're locked in now.
We got locked in now. All right. Ta-da. We gotta multiply these. For the exam, don't worry, we're not gonna ask you to multiply matrices. It's a thing that you ought to get agile at, but it takes a bit. But actually, a way to simplify multiplying two matrices is just to look at the second one as columns. Anyone have an intuition for multiplying these guys? What it would look like? Well, first off, what are the dimensions of our result going to be? 2 by 2. Okay. The first column of the result you're going to get by doing what? dx dt times this column. That's a bit messy. Let's go with the dot product approach. What was the dot product approach? The row picture, right?
Yes.
Yeah. So the first row, first column of the result. Actually, I need to make this much bigger, just to make room for all the terms. Okay. I feel like this is like, yeah, like this is like a microphone. Exactly.
Hey, at least you got it.
It's, what's it?
He's it.
He's it?
Yeah.
You guys are playing tag?
We've been playing tag for 5 days.
Alright. Touch each other too much. What do we have? So, du dx.
Times dx dt.
Times dx dt. Plus
dy
Well,
dt.
du dy times dy dt. I'm a pain in the ass. Okay, what am I here? So which one do we do next? First row, second column, or first column, second row? Second row, first column.
Second row first.
All right, what do we got now?
dv dx times dx dt
Okay.
plus dv dx times dx ds.
dv dy.
Oh.
Yeah, times, yeah, the v's and that's a y. dy, that's all right, sorry.
That's my sign.
All right, next, someone else. du dx, all right, Lily. du dx, dx ds plus. Okay. And even if you don't look at them, you can kind of figure out what the next one is, right? What is it? No, I kind of want to look at it. Never mind.
Come on, Thomas, you got it.
Second row, second column. Yeah, Thomas Summers, what do you got?
What happened?
Exactly. Second row, second column. Which one are we going to dot?
No clue, sir.
Second row of this guy, the second column of this guy. That's all right. That's all right.
dv dx
Okay.
times dx ds,
Mm-hmm.
and then dv dy and dy dx.
Okay. Now we can start abusing notation, sort of. du dx, du dt, sorry, du dx, dx dt, what does that give you a sense of? What does that boil down to? The dx is canceled, so you get du by dt. What happens here? Du by dy, dy by dt. Y is canceled. So is this 2 du by dt? Question mark. Or is there a conversation we briefly had last time that might shed some light?
No. It's not two. They create. Contribute to the whole.
Yeah.
There are two different parts, yes. Components is a word for it. I'm afraid because then I think of vectors, but yeah. This is the way that u changes through, this is the way that t changes u by way of x. It's not the total contribution. This is the way that u changes, this is the way that t changes u by way of y. So these are individual contributions, and this whole piece adds up to du by dt. Okay, what happens here? Du by dx, dx by ds, what does that mean in English? What is this dotted line crossing? Because it's not really crossing out. What does this mean in English?
Evisceration.
Evisceration, decapitation, commiseration, Ooh, I'm gonna write a rap song during this exam. All right, but what is this? This is du dx, dx by ds, so what does this represent? Du ds, with a caveat, what's the caveat? The what? By way of x, yeah, sure. So, and then this same by way of y, so what is this term? Du dx, okay. Bottom one, at this point we can start to infer. dv dt, and du
Building occupants. MIT
yeah,
Electrical
dv dt
Services
and
will be
dv by
conducting a
ds.
test of the building fire
So
alarm
this whole
system.
thing,
Unless you
boils
are
down
instructed
to,
otherwise, please disregard
du
all fire alarm
by
alert tones,
dt,
voice messages,
dv
and
by,
flashing
du
lights.
by ds,
At the conclusion of this testing,
dv
an
by
announcement will
dt.
be made to indicate
by
that all
ds.
fire alarm testing
What is
has
this
been
if you wanted to write
completed.
it as a Jacobian or as a derivative? This is d what?
Attention
dy.
building occupants. MIT Electrical Services
UV
will
over
be conducting a
TS,
test of the
otherwise
building
known as
fire
a
alarm
Jacobian.
system.
uv to.
Unless you are instructed otherwise,
So
please
what we have
disregard
shown
all
is
fire
that we
alarm
can chain
alert
these
tones,
Jacobians
voice
along
messages,
to
and
get
flashing lights.
the derivatives
At the
down the chain.
conclusion of this testing, an announcement will be
We can
made to
change the
indicate
Jacobians
that all
along
fire alarm
to get the
testing has
derivative
been
of a top
completed.
level variable with respect to a bottom level variable.
Attention
Yeah.
building occupants.
So order matters
MIT
because you
Electrical
have to go
Services
from
will be
UV to
conducting
XY,
a test
not
of the
XY to
building
CS.
fire
So
alarm
we're
And solve the
system.
matrices in there.
Unless
think
you
if
are
you try
instructed
it,
otherwise,
something will
please
go wrong.
disregard all fire
Yeah, I
alarm
get
alert
you.
tones,
What is the addition
voice
though?
messages, and
What are the
flashing
addition?
lights.
In the dot product, what is
At
the
the
addition
conclusion
there?
of this
Oh,
testing,
but you see it here,
an
this
announcement will be
addition.
made to
So you're saying
indicate
how
that
to
all
go
fire
from
alarm
this to this?
testing has
Yeah.
been completed.
Yeah, remember though, that, so that's the bit, is du by dx, dx by dt, that is not du by dt. Because if it did, then you would get 2 du by dt, right?
Yeah.
But instead, this is the partial contribution. This is the partial piece of du by dt through x,
Oh.
right? It's like, let's see, anyone here with, sorry to bring up things, but anyone here with divorced parents? Who like spend
I can
weekends?
act like I have divorce parents for the analogy.
Okay, sure. Are you okay with that?
No, I'm good.
You think it would be, oh, you don't have divorced parents? I think.
Oh, got you.
Got it, okay. Well, they're getting the process. All right. No one. You go see your dad on the, I have divorced parents. I went to see my dad's a character. I would see my dad on the weekends and my mom during the weekdays. It's recording. No, caballero, come on.
Just for some mic.
No, yeah, ha. Oh, that was good. I didn't see that right away. Like the thing that how were you impacted by
Attention
food?
please.
Jesus Christ.
Yes, so let me-
The signal tone you have just heard indicates a report of an emergency in this building. Please walk to the nearest exit and leave the building.
Why isn't this happening during the exam?
Attention please.
Yeah.
Do you all have
The
memorized
signal
this?
tone you have just heard indicates a report of an emergency in this building.
On the speakers during the
Please walk to the nearest exit and leave the building.
Then how else are they gonna know?
Okay.
Attention, please.
Are you still playing?
The signal tone you have just heard indicates a report of an emergency in this
All right,
building.
I'm gonna try. You ready?
Please walk to the
Okay.
nearest exit. and
You are
leave
affected
the
by the
building.
food that you eat. I ate very differently at my mom's house than I did at my dad's house. So if I wanted to find, every time I try, it gets worse. Okay, this is not Mississippi. It's okay. But I'm gonna look at outside because I don't. This isn't actually.
Okay, but Ron, they create a partial on each.
No, que cosa no digna.
Just rewire it.
Where can we flee to hold this class?
We can go outside.
Can I teach the rest of the topics outside? I'm considering it. No, I wish I could, but we need the board space. All right, guys, so if you like Jacobians, cool. If you don't like Jacobians, that's okay too. There's another way to do this. Are you ready?
Wait, what about your parents?
Oh, sorry. Okay, I didn't know if you were happy for the honest. You're affected by the food that you eat, right? So, hey, I was going to answer your question. That's right. You're affected by the food that you eat. So if I try to figure out the rate of, if I try to figure out how you're affected by food, I need to account for the part that is food by way of your dad and food by way of your mom. Does that make sense? Or, you know, trying to be non-normative or something. So like you could have two moms or something. Yeah. Cool, it's wonderful. It's a wonderful world. All right, any questions? Do you understand the derivative analogy that okay, I didn't break math. Okay. So that's why this whole thing adds up to you du by dt, not the individual. Okay. Now, having done this, I get to tell you about an easier way to do it.
Ooh.
Yes, if we ask you for Jacobians, use Jacobians, but also let's say that you have the following. You have f, and what variables does f most immediately depend on? X, y. What do x, y both depend on? T and s. You can write it like this, or you can just consolidate them into one t and s. But the point will be very intuitive, I think, once we draw this out. What is df by dt? What you're going to do is you're going to circle f, and you're going to circle your t's. And you're going to draw a path, every possible path from f to t. What's the first one you see? F to x, and then x to t. Okay, so that's df by dx, dx by dt. So df by dt is df by dx, dx by dt. Beautiful. Okay, are we done? There's another way to get to this, right? This is what you're eating at your dad's house. df by dy. So my mom's Cuban, my dad's Venezuelan. My mom, like many Cubans, fries everything. And my dad is a personal trainer. So that meant that my dad tried really hard to get me to eat healthier food than my mom was able to put out. So he would give me lunches during the weekend and I would eat them during the week. I was on a meal plan. Yeah, my mom was pissed. But they get along wonderfully now. Okay, does everyone see what I just did here?
You took the partial of
Mhm.
this food that you got from your dad and the food that you got from your mom.
Yeah.
And now you're adding together to say how much food you actually got.
Right, so this is not 2df by dt.
Don't worry
Questions?
about it. You're thinking.
All right.
You know what? I'm thinking too much. I need to turn off the brush. Stop
Yeah.
worrying your
Ah. Oh, I have a secret about sandwiches I'm going to share with you at some point. Anyone in the subreddit Unethical Life Pro Tips?
Yeah. Find out now.
Yeah, the camera's rolling, so we'll chat later. Okay, so, what if there are more layers? What if there are more layers?
It would still be the same thing. You still have to do your
You keep going, right? How many, if, let's say there were 3 layers. So there was x, y, ts, and ts were functions of q and p. Then what else would I write here? dt by dp or something, if you have things multiplying. Believe it or not, this is how AI works. But we'll chat more about that at some other point. Okay, questions, you guys?
6, 7 virus.
Any more questions?
What's the application actually?
Ah, well now I have to talk about AI. All right, how does AI work? AI works by simulating your brain. In theory, other than when we're on Instagram, our brains make a deep set of connections from one layer to another. And to track how one thing over here affects your brain's decision to go buy a sandwich way over here, you need to trace down all the possible routes. That's what this is. This is your ultimate decision, and this is the neuron that triggers your fundamental fight or flight response. And this is the neuron that triggers your insecurity when you go on Instagram, and this is the food. So what I mean is there are layers, yes? Like an onion, it's Shrek. So this is me talking about that. T, then X, then F.
You still have one?
I'm being like
No,
a
that's
psychoanalyst in
not
this class, talking about
perfect.
divorces and
They started
food and
doing it
Instagram. So we're gonna move on. Are there more questions? Okay.
I hate doing that.
Yeah, hi.
Is it, are they like the DF,
Uh-huh.
DT, that's in the X direction, is that like, what's that?
Yeah.
Is there anything like that?
Oh.
Because I'm like,
Yeah.
I'm getting at like when you're finding like a total magnitude or something, you don't you add like square things?
Oh, I see what you mean. Yes, so guys, when I say components of the derivatives over here, it's very different from what I mean when I say components of a vector. It has nothing to do with direction in that sense. We can make a case that it kind of does, but no. It's all scalars. Make sense? Okay, more questions.
What now?
What now? Well, what's now is our last topic that could possibly be on the exam.
Green's theorem.
No, you don't want that. All right. Any questions?
a little
on this?
early.
Maybe we could. You know what? Maybe we finish early. Let's see how. Let's 5 it up. Because you guys are tired, yeah.
Right.
You need time to have a food coma before chemistry.
How do we even explain
So
the
Ken Alley just
concept like
whacked
that?
me in the head with it.
Thank you, thank you.
All right. No, chemistry's gonna be fun today. I have a feeling. All right. Can I erase that?
Tonight's gonna be a good night. Tonight's gonna be a good night.
Yeah. If you have Chem Patty, I'm not worried because Chem Patty is very loud. So you could be in coma and you wake up.
This is not true.
Okay.
As someone who's taken Patty. Shh.
Okay, so now our next section is more on approximation. Not to be confused with moron approximation. Okay. And to do this, we're going to circle back. We're going to, ooh, jargon. Have fiery passions, which I hate jargon. Jargons everywhere. I tried to not create too much jargon, a mess of jargon in this class, but like, you know, like the fitness bro jargon, like 7 reps, and what's the other word?
7 reps.
Yeah, I guess that's not so bad. Why should I be so pissed? Yeah, stuff like that. Or when you're climbing, there's so many words for this. I'm going to beta this one, and then you send it, and then you something. Anyway, I don't know. I think I have an exaggerated aversion to jargon. But when I worked at a biotech startup, we had this one man. His name was Tawanda, and Tawanda, it seems, was adopted by a family of product managers when he was 3 and raised by them, and only could speak in product management terminology, which means everything used the words circle back. What else do we have?
Streamline.
Streamline.
Can we white ballot this?
What else do we have?
Not my tempo.
What?
Not quite my tempo.
Not by my tempo. Okay, not quite my tempo. What else do we have?
Optimization.
Yeah, KPIs, key performance indicators. What was that?
B2B.
ID what?
B2B.
B2B. Ooh, IDGPETGAF. That one applies to
I
anything.
don't give free.
Paid enough. Paid enough.
Data.
Yeah, that happened. That was not a project manager. Anyway, I promise there was a reason I was bringing this up, and I'm starting to lose it. Why was it?
Approximation.
Why did I start?
Approximation. That's all it took? Is the word circle back to come up? I must have some serious trauma. No, this guy, you'd ask him a question and he wouldn't respond in English. I read somewhere that a project manager is someone who thinks that if you get 3 women together, you can make a baby in 3 months instead of 9. So I fear project managers and I fear jargon. Okay, more on approximation. More on approximation.
Oh, wait, the integral.
No integration yet.
The graph.
But we're going to integrate our assets so that we can solve this. So here we have it. Here's a function. I'm going to use it in orange actually. Okay. Here's a function. And I have a particular point here called P0. And linear approximation, this function is, y equals f of x. We love y is equal to f of x. And we also love doing our approximations in green. Not because it's Green's theorem, sorry.
No.
So we have our point P0. Linear approximation said what? In single variable calc, what were we doing? Tangent line over here. All right, Leanna, what else? What do we do with that tangent line? Yeah, so we have x, we use a small, but like big picture, yes. Our tangent line approximation was saying that f of x is approximately f of x naught. That x naught is this point over here. What else goes here? F of x plus, and then what we go here?
F prime of x.
F prime of x naught.
Minus.
Times, yeah.
X minus x naught.
Brilliant. This is single variable calc. That's all it is. And so actually, you have seen this before we even talked about a gradient, right? This is that. Or another way, the cool way. I mean, it's not so cool. Okay. Another cool way to say it is f of x naught. So f of x is about f of x naught, or f prime of p naught. Well, p naught, yes, yeah, I understand that. F prime evaluated at that point, p naught, plus f, what am I doing? F of p naught plus f prime of p naught delta x. Wow, that was a lot of work. Okay. Does that, you see how these are the same thing? It's just at that point, yeah, so f of some other point x is f of p naught times delta. Now, we did this in a more general sense using the gradients for functions of multiple variables, functions of multivariable variables, which is kind of ridiculous. Because in Calc 3, we said that f of x, some multivariable position, right, is f of x naught plus, and what was our really compact way to write this that had no specific number of dimensions to it?
Oh, no, f and f to the nth derivative, right, over n factorial.
Oh no, you're thinking Taylor approximation or something. You hang tight, mister. We're gonna do that in a second. F of x, what was the Calc 3 way to do it? Yeah, Bon.
Something times a vector.
What was that?
Is it something times a vector, right?
There are vectors in there for sure. What's our favorite operation to do between vectors? Dot product. So it's the dot product of the gradient,
Oh, the direction.
right? Gradient dotted with what?
X star.
Well, not x prime, delta x vector. So, hang on, now let's do
Oh,
this.
yeah, I got that. Oh, which is our top.
Yeah, x, I'm going to be consistent over here. Okay, so what does this boil down to in the tangent plane approximation land, right? This is z naught plus the gradient, so df by dx times delta x plus df by dy times delta y, right? This is the same thing as saying f of x naught y naught plus df by dx evaluated at p naught times x minus x naught plus df by dy evaluated at p naught y minus y naught, right? And that was f of x y. That was our approximation. This should be an approximation. This boils down to this. Does that ring any bells? You guys tired? Yeah, it's a rough day. This again? Yeah, that boils down to equation. Yeah, Diego, you got it. Diego, right? I remember you, Diego. Okay, so yes, this boils down to tangent plane equation. But you can use the tangent plane equation for linear approximation, provided you stay close. And that's exactly this idea in single variable calc. Okay, I want to add a term because someone wanted to talk about Taylor's series. Who was trying to get us over there? Who's trying to drive our KPIs up? Who's trying to raise shareholder value by raising productivity and yield? I think it was the fellow who's perspiring over here. Yeah. All right. So let's do that. Let's level up.
Oh, man.
It's because we had Taylor Swift in of our life, guys.
Yeah. So this was called linear approximation. Why? This isn't a line, it's a plane. Why is it called linear approximation?
Because we named it wrong. It's actually linear approximation.
It's no, actually, so that's the magic. What's a linear equation? Yeah.
That's just to the power of 1.
Exactly. Whenever we have variables raised to the first power, first order equation, that's a linear equation. I mean, unless it's like x over y or something. What I mean is just like sums of basically linear combinations of the variables. Okay. So now I'm going to do quadratic approximation. What do you think that means?
X squared.
X squared, second order approximation. When you go into Microsoft Excel and you get given some data, you can fit it with a line. You can also fit it with a parabola. You can also fit it with a third order equation. What happens when you add more and more orders? It gets a lot more wiggly, right? And it starts to overfit your data because there's no way that accounts for school cafeteria lunch trends. They didn't think it through that much. Okay, so this was linear approximation. Now we're going to talk about quadratic approximation. And quadratic approximation unlocks a world of cool properties that are going to jump out. So, quadratic approximation in, do this part in white, in single variable calc. So in calc, A, B, C, that's really what this should be. It's 2D, I start to get into trouble when I'm thinking about dependent variable in calc, A, B, or B, C. We're in good shape. Okay, in calc A, B, or B, C, what did that look like? Well, again, this same function, I'm going to actually do this here. I need a color for the quadratic approximation, and it's going to be amarillo. Okay. Linear approximation to the function at this point is the tangent line here. What do you think the quadratic approximation to this function at this point would look like? Yeah, one. Yeah. Like if you would draw it. So the quadratic approximation to this function at point P naught. Yeah, probably something like this. And hey, that does a pretty good job of capturing the behavior of our function near P naught. Yes? So this was the linear. I know.
It's like having a baby.
I mean, it's better to do it now than the semester, but this is our semester. Okay.
And that in
Attention, please.
F of x.
The signal tone you have just heard indicates a report of an emergency in this building. Please walk to the nearest exit and leave the building.
Who's watched The
Attention,
Office?
please.
Yeah, the
The
boat.
signal tone you have just heard
the first
indicates
season,
a report
the party
of an
boat, the
emergency
party
in
cruise.
this building.
Where he takes over the mic
Please
and
walk
he
to
says,
the
"Attention,
nearest
everyone!
exit and leave
I haven't
the
heard
building.
it. The boat is sinking." And like there's one guy
Attention,
who
please.
already starts jumping out the window of
The
the boat.
signal
and
tone
I'm
you
thinking,
have
I'm
just
gonna do that
heard indicates a report of an emergency in this building.
Huh?
Sounds good to me.
Please walk to the nearest exit and leave the building.
Oh, by the way, there's a really pretty courtyard here that few people know about.
I love this courtyard. It's so
So
wonderful.
that one set of stairs and there's a door. Yeah, it's not so well known. If I had a whiteboard, I think I totally would. Maybe I'll figure that out for class. Let me put that on my list. Alright, we're gonna wait for that to pass and then we'll be good. Yeah, I know, I'm sorry. I was kind of looking forward to that too. I was up to like 3 writing the test. It's gonna be fun. If I had that much fun writing it, and I don't get off on being diabolical, you know what I'm having fun. Oh, I have one of those. It makes that sound. Oh, that's good. I think that's it. It was resolved. No. I had a
May I have your
hard.
attention, please? May I have your attention, please?
See.
This is a reminder that MIT is testing the building's fire alarm system. Please disregard all audio, visual alarms. May I have your attention, please? May I have your attention,
Yeah,
please?
we know.
Please disregard all audio, visual alarms. We are testing the fire alarm system at this time. Thank you.
You can start writing and doing it after.
Is that okay? I'm actually going to do the following. I'm going to write the quadratic. Ay, Dios mío! I'm going to write the quadratic approximation piece in yellow. So we're going to expand. The linear part is green. The quadratic term, when we add the yellow, it will make it a quadratic approximation. Give me your best shot of single variable. Taylor something or other. That is. Quick, for the fire alarm.
F of x double prime.
So is the coefficient in there?
Yeah. Yes.
1/2?
1/2 f
Yeah.
double x
F double prime.
of x naught
Uh-huh.
times delta x squared.
Yes!
What? Does that even mean?
It's actually 2 factorial. 2 factorial.
Yeah, technically. Yeah. Well, I'm not gonna, yeah.
We're not gonna expand past this.
X, well, no, we will, but hang on. Okay. Where does this come from? Vaughn, you made a face. It's, remember Taylor polynomials? Taylor expansion? basically, it's an equation to come up with how to approximate a function at a point in first order, second order, third order. What's the general form of this, by the way? I don't remember completely how to do it off the cuff, but you all might.
F to the n derivative.
So f of x is approximately, what is it?
Summation of f of n.
F of n. F of n?
No, f to the power of
Oh,
n.
f of the nth derivative of x, of x naught. Yeah, divided by n factorial. Where does n start? 0? To whatever you want. K, the kth approximation. Did I get this right?
Yeah.
Okay.
X minus x.
Oh,
Oh,
yeah,
yeah,
right.
To the n. Okay. That's Taylor, for whom buildings are named in this school.
And how we're doing is doing that.
Or McLaurin. Oh, I haven't started with McLaurin. All right, questions, guys? Vaughn, does this sort of remember me? Wait, Vaughn, speak up, I can't hear you.
How did we get from that thing to that thing?
Yes, okay, so what's the, when n equals 0, what is this? This is just f of x naught
Oh, wait.
times 1, and that's just 0 factorial to 1. What then, when n equals 1, this is the first derivative times x minus x naught over 1. What's the second term?
And then that's the.
Second derivative times difference times the delta squared over 2 factorial 2, which is 2. What's the cubic term?
F third derivative.
Third derivative times
X minus x naught.
cubed over. What do we know? But this is, I'm glad you brought this up. Guys, as n gets bigger, as we try to do the higher order approximation, what does the significance of that, of each bigger term do?
Less and less.
Less and less, we're adding a smaller number, right? You can get a lot of your approximation done with linear, and almost all of it done by that point once you go quadratic. Okay, questions?
How does that?
Yeah.
How did they derive n?
Because you have to multiply quadruple. But like reverse quadruple.
Yeah,
Integration.
there's a thing, I actually don't remember the date. But if you want to work on it after class, like I'm sure we can figure it out. All right. Okay. We're going to work on quadratic approximation, which means we need to add one more term over here. So this is the single variable version, and now let's also add the cool way. So this is f 1/2 f double prime at p naught delta x squared. Okay. This is how we go quadratic, and what I'd like to do is show what this looks like when the case where we have a multivariable function. Okay, so in Calc 3, this was the linear approximation. We need to add the quadratic term. So we do a plus, and what do you think goes here? What's the first? If you knew nothing else, what should go here?
Vector.
Even before that.
1/2.
A 1/2. Okay, cool. You already got like a third of the points on the test. Okay, 1/3. And now here's the question. This was our first derivative of our function, right? The first derivative of a multivariable function is it's a vector value function called the gradient.
Why?
Oh yeah!
The Hessian.
I thought it was a little placement.
No, that's Scalar. That's Scalar.
All right. Yeah, well, all right. Hang on. I'll make sure we're all on the same page because we're about to drop some bombs. Okay, not so bad. Okay, linear term, right? 0th derivative is just the function. First derivative times the change to the first power. And now we need, well, if we have first derivative here, what do we have here? Second derivative, right?
Jacobian.
Yes, the Jacobian of the
The great.
the Jacobian of the gradient, right? Because the gradient is a vector value function, yes? So we need to put here our second order term, 1/2 j of grad of f at p naught. And then what goes in here? Delta x vector. Well, this is first power, right? So what's this?
Squared.
Second. Now this is the part that we need to talk. We need to talk. Because we need to break up with our notation when we're doing it. That's what we need to talk about. So I would like to now dissect this quadratic term. Are people with me? Are we good? We don't have to be. If you told me right now, Christian, none of this makes sense, let's go back, we'll go back.
Well, 'cause there's
The
no-
fire alarm will probably start ringing, but we'll go back.
Does this work for like multiple dimensions or like
Yeah.
all dimensions?
It does, and in fact, it is about to because f is a function of x and y, for example. Yeah, David?
After you're done, are you gonna generalize it? But you have a problem.
No, but tensors, you want to do tensors, alright.
Are we expected to be able to compute a quadratic approximation?
Hi, Susan, it looks like I just struck you with lightning. Okay, we're going to clean that up in a moment, so take that with a grain of salt. I don't Oh, okay. Wait, you mean here? Or there? The yellow. Oh, no, you're right. If I'm going to keep consistent with my notation. What is x times? It's a vector with my coordinates. Yeah. Okay, thank you for catching it. Okay. Keep asking. I think we need more questions before I go further. So please ask more questions. Yes, no.
But we're just saying the Jacobian as a shorthand for saying we're doing the grad twice. If we have to do it 3 times, we have to say, can we do it 3 times?
Yeah, it's called a. Instead of, you know how a matrix is a rectangle?
Yeah.
This next thing is a rectangular prism. It's called a tensor. We're not going to do
We're
that.
not doing tensors.
We're not doing tensors. No, let relativity kick you about with that.
Do we have to, is there a quicker way to do this, or do we have to do the Jacobian for that?
I promise it will be clean. So that we're going to handle. We're going to attend to that. What other questions? Come on, guys, you got questions. You're asking each other questions. So
Can you go back to the y?
yes. Taylor series, right? First derivative, second derivative. Right? The derivative of the first derivative, basically. The derivative of the first derivative is the derivative of the gradient. The gradient is an example of a what value function. So how do you think the derivative of a vector value function? The Jacobian, the gradient of the rows of the vector value function. But yes, the Jacobian. So this is the Jacobian of the gradient. Okay, more questions? Yes. Come on, you guys got this. None of this is supposed to be obvious. Yeah, hi Sylvie. I missed you. Thanks.
Can you try to make it visualize in 3D?
Can you what?
Can you try to visualize in 3D for me?
You bet.
Yes!
I can do a crappy drawing.
Or we can look at it on a graph.
Yeah, I can do it on a graph. I have lately been watching Bridgerton with the redhead. It's awful. But instead of Bridgerton, sometimes they say Bridgerton. So when you said graph, I thought, graph.
Have you guys ever seen this movie, DMC?
Yeah.
There's the
Oh, but that's in the film report, but that's okay.
yeah, the other
You're not going more than Bridgerton?
the drama.
The drama, right. Yeah, 'cause it's all about gossip. All right. Oh, I plugged in the computer. Yeah, that's not good.
Did I just skip that one?
Oh, right. How are we doing? I think we. Oh, welcome. Okay. So we're going to go to the grapher, and I'm going to plot a function in free space. I'm glad you asked to visualize this. This will be fun. So the function is x squared plus 3xy plus y cubed. So this is all kinds of messy. Let's find the equation of the tangent plane. You guys gonna work that out? The little whiteboard, so you want me to just plot it? Plot it? Okay, that's okay. Okay, the equation of the tangent plane ends up being 8x, so it ends up being z is equal to 8x plus 15y minus 23. That is tangent at this point. It's really hard to see on this graph. Smart move, let's do it. Is that kind of yeah, and it merges with the green. So this is oh, lights in the classroom? Yeah, actually, could we get the lights? Can have it a bit closer or oh, there you go. Thank you.
Make it like a
Oh, yeah. Blue and
like light blue.
yeah.
Yeah, that's yeah.
Okay, that's manageable. So do you see that we have our tangent plane over there? It's tricky to see because it's so stretchy. But it does only touch it at one point. Okay, you guys can follow that, sort of, you can see it? Okay, now let's do the quadratic approximation. If I plugged in my quadratic approximation, which I need to finish telling you how to do, but that function looks like x squared plus 3xy plus 6xy squared minus 12y plus 18. And if I plot this in yellow, that's our color, we like Coldplay, okay, then this is what it looks like. Now, why is this useful? Because
Building occupants.
I know.
MIT Electrical Services will be conducting a test of the building fire alarm system. Unless you are instructed otherwise, please disregard all fire alarm alert tones,
6y squared.
voice messages,
There we go.
and flashing lights. At the conclusion of this testing, an
There we
announcement
go.
will be made to indicate that all fire alarm testing has been completed.
They intersect at the point of, I think I must have
Attention
missed the
building
function.
occupants.
Minus 12.
MIT Electrical Services will be conducting a test of the building fire alarm system.
I think I might have gotten the offset
Unless you
wrong,
are
but
instructed
give me one
otherwise,
second. This color
please
is all-
disregard all fire alarm alert tones,
Please, I'm very
voice
disregarding
messages,
that.
and flashing lights. At the conclusion of this testing, an
So the
announcement will be
quadratic
made to
approximation is a
indicate that all
parabola.
fire
You see
alarm
the
testing
parabola up
has
here?
been completed.
That intersects the function only at that point of tangency. And what I'm learning here is that I
Attention building
calculated
occupants.
the y offset, is
MIT
the offset
Electrical
wrong?
Services
What do
will
you
be
think this
conducting a
bottom of
test
the
of
yellow
building
should be?
fire alarm system.
Well, at the bottom of this guy, yeah.
Unless
so
you
maybe
are
that's
instructed
right.
otherwise, please disregard all fire alarm alert tones, voice messages, and flashing lights.
People
At
the
the
bottom of
conclusion
the
of this
quadratic.
testing, an announcement will be made to indicate that all
Yes.
fire alarm testing
By
has been
definition,
completed.
right? The approximation touches it at the point that you're trying to find it. There we go. Okay, so here's our quadratic approximation. You see how it hugs our function, the quadratic approximation, which is yellow, it hugs our function at the point of tangency. And then it goes off and does its own thing. If we zoom out, it's not going to follow the function exactly. But at the point of tangency, it does a really good job of approximating. Does that make sense? I wish this was a better, some of you need to, if you actually said decimals, you can clean this up. Okay. Questions? Do you understand what the quadratic approximation does? Yeah? Okay. I would now like to spend the next 10 minutes, sorry, we couldn't end early, but detailing how this is calculated. But does the principle make sense? We went to tangent plane, which was over here, and now we're going to go to tangent line. Okay, so, could we get the light back on? And the projector screen up so that I can draw on here. So this part I'm going to put in quotation marks because we need to clean up the notation. Maybe if you go to the media console, there's a projector. Actually, I can just unplug. Oh, no, it worked. But we can turn this slide on too. Okay. So, this is what it was. This is what we have. The question is, what is the quadratic term? Term in multivariable calc. The answer is as follows. We are used to seeing for an equation a linear form. So a linear form takes the form a dotted with x, right? A vector of coefficients, a1 x1 plus a2 x2, so on and so forth. You agree this is linear? Okay. Quadratic form, in linear we have a vector. In quadratic we're going to use a matrix. It's going to be x transpose a x. This is the full version of ax squared. We just won't write it that way because that's not how matrices end up working.
It's just like the B set.
Yeah, wait, what is it? X trans? Yeah. That was a quadratic form. Remember, guys, summer is pretty low pressure, pretty low, not low pressure, low stakes. When you go see this in 1806, you'll be like, I remember that one pesky piece of problem. You'll be less scared of it. All right, so that's quadratic form. So I bring this back up to ask you, this 1/2 Jacobian times delta x squared, what should it really look like? 1/2 delta x transpose, Jacobian of gradient, delta x. Okay, so this cleans up, but we're not done. Because we got to figure out what the Jacobian of the gradient is. So this is 1/2 delta x transpose. What do we say? Jacobian of gradient, delta x vector. Okay. So let's talk about what the Jacobian of the gradient is. Okay, the Jacobian of the gradient of f of xy. That's another way to say that's the Jacobian of, what does grad of f of xy look like as a vector? What are the components? It's the Jacobian of y. What's grad of f? Well, what is grad of f of xy?
Partial derivative.
df by dx, and then?
F dy.
Okay.
Everything is Jacobian in respect to x and y.
Yeah. So what was Jacobian? Remind me. What is the Jacobian? What are you doing? The gradient with respect to the rows, yes. So the first row of this is grad of df by dx. And the second row of it is grad of df by dy. All right, we're going places. What does gradient mean? First you're taking the x derivative, and then you're taking the, right, okay. So what is the x derivative of df by dx?
df by dx, dx.
Yeah. Or d squared f by dx squared. What's this called, by the way? Second derivative. It's the partial in x of the partial in x, the second x derivative. Okay, what is this term? What is this term? You're thinking d by d what of df by dx?
D by dy.
D by dy. So this is d squared f d dx dy. Okay, what's this term over here?
D squared f.
Uh-huh.
dy.
dy dx, right?
Yeah.
And what's this last one? Notationally, this is the same as fxx, fxy, fyx, sorry, fyx, fyy.
Is fxy and fyx equal?
It turns out, the second partial, doesn't matter what order you take it in, it's the same exact thing. Yes?
Is it because it's continuous?
Yes, if the function were messier, this starts to break down. But then we won't work with that. Yeah, no.
Okay, so like, when we're taking the gradient vector, that has like an x and y component, right?
Yes.
And then you derive the x and y, the partial derivatives with respect to x and y of each component.
Yes. Yeah, I mean, pretend this is called u, right?
Yeah.
And this is called v. And you would say ux, uy, vx, vy, right?
Yeah.
And if u is fx, then ux is fxx.
Can you say that again?
Yeah, you bet. Okay, let's say that fx, df by dx, let's just call it, we're going to call this u, and we're going to call this v, right? So you agree that the Jacobian would look like ux, uy, vx, vy, right? That means du by dx, like the subscript means the derivative. Okay, so if ux is itself, sorry, if u is itself fx,
Okay.
then
yeah.
ux is fx x.
Okay.
Derivative of the derivative. This is our second derivative matrix. And it has a name. It's called the Hessian. This is the Hessian. It is the second derivative matrix. So second. Okay. So in general, if f is a vector value function, I'm not talking about the gradient right now, I'm just talking about f. We're going back to what we were doing earlier. If f is a vector value function, its Jacobian is just a Jacobian, right? But if f is a very specific vector value function called the gradient, its Jacobian is called the Hessian. Just a bit of terminology. So that's what this is. Okay. And the second derivative term, the quadratic approximation, comes as follows. 1/2 delta x transpose. So we can fill this in. This is no longer Jacobian of gradient. What do we have in the term for that? H. The H. And where are we evaluating the H? At x naught, at that initial point. Okay. Just like we did in single variable calc with our second derivative. That is our quadratic approximation. Okay. In the notes, which are on the canvas, there is a practice problem with this, and it would be wonderful for you to give it a shot. Consider it an exam practice problem. Wink, wink. Every now and then I get chalk in my eyes and I start winking really hard.
Wink, wink.
Yeah, like, I don't know, I got a lot of chalk in my eyes.
Do you have to nudge someone as well? Or?
I hope I don't have to. I hope you guys got straight smarts. So please look at the notes for an example problem. That could be helpful. Here's a question, guys. Go back to single variable calc land. Let's say that my function was, well, my function in orange, the function that I'm trying to approximate, was linear. Okay. What would the linear approximation of my function look like? Itself, right? Because it's already linear. Ah, my eyes. My eye is itching or not. I don't know why. Okay. Cool. Yes? Oh, I mean, yes. But I wouldn't view it as, it's not the result of a chaining so much. It's not the result of a chaining. What was that?
Is this coincidental to squaring it? Like it just happens. Like this, if we did 3, it would.
If you do, yeah. Okay, more questions? Yeah, you got it. Oh yeah, that's right, useful. Guys, what is delta x? What is delta x? When I keep writing this delta x vector.
Your x and your y component, or your x, y, z component. Right,
so it's delta x comma delta y comma delta z as a vector, yes? Okay, what is the transpose of a vector, of a matrix? And what is it?
The vector is a column, the transpose is a row.
Exactly, so if x is x, y, z, x transpose is that as a row, x, y, z. And this came up, I believe, in the P set, which is the following. X transpose y, right? Or yeah, well, let's just do x transpose x, sure. That is what? It's the row x, y, z dotted with the column. Sorry, multiplied by the column x, y, z. Spoiler alert. What does this multiplication look like? X times x plus y times y plus z times z. What is that the same exact thing as? It's x dotted with x. This is 1802 language. This is 1806 language. And in fact, in the most general of terms, if you have a vector A dotted with a vector B, this is the same thing as A transpose B. You pre-multiply with the transpose. So that might give you a sense. Again, x squared is like x dotted with x, but we have a matrix, so it's x transpose AX. That's how it scales to quadratic form. All right. There's a third order term.
No.
We're not going to do it. Yeah, okay, cool. Yeah, you want to come in next year. We'll save it for next year's video. Okay, questions and we're good? I have to be. I'm glad you used the markers. I feel like it's a useful place to be messy math when you do one. All right, guys. Wipe the board and bring it to the front, please. Thank you. This is great. Wow, that was. I'm so hungry.